All right, so the first line. So I'm actually starting at the beginning of the chapter now. I know we've jumped around a bit. So one of our objectives is to outline, right, all the essential components, basically know all the essential components of the innate, part of our defenses. And so the first line defense is your anatomical barriers, and I should have here antimicrobial substances as well, that we're going to talk about. So notice that's in bold because we haven't talked about that yet. The sensor systems, which are underneath the first line, we have talked about, right? These pattern recognition receptors, they're going to help us sense when the bad guys have arrived. Where are these receptors? Where are these receptors found? Some of them, but the actual receptors. Where? Cells. Yeah, so be more specific. Where on a cell? So give you an example, a toll-like receptor, an example of a pattern recognition receptor. On the cell wall. Is that it? In the cytoplasm. One more. Nope. Endosomes within the cell, right? Those lyses, those phagosomes that we form, phagocytic cells form. What we haven't talked about as far as receptors is interferon response, which is a little bit different than pattern recognition receptors. Do you guys remember what the major outcome, what was normally happened when, like especially phagocytic cell, if one of those receptors got triggered, that basically said a bacteria got in. It's going to send signals, and what's the most common response for the immune system? Inflammation. Someone's been paying attention. Cool. So a little bit different response for interferon, which is response to viruses. Okay. The complement system we haven't talked about yet. We're going to talk about that today. We have talked about phagocytes, right? Our phagocytic cells that can do phagocytosis. We'll review that in a moment. We've talked about cytokines, right? These are those chemical messages that the cells use to communicate with each other, i.e. the hormones of the immune system. We've talked about inflammation. We started out with inflammation. And today we're going to talk about, and we're going to end with fever. So let's review just a little bit. So I had posed this question by itself. What are the common bacterial molecules that toll-like receptors recognize? So maybe if you were up late last night, you might have wrote yourself a list. Probably not. So I changed it to a multiple choice question so we can ask it on Poll Everywhere. So those of you guys that are just coming in, right, we're going to switch over to Poll Everywhere. Let me go to my polls. And you'll type in poll. Here, I want to get this one published first. So I got to remember how to do this. Click that button, right? I think. So you can either text or you can use your web browser on your smartphone. If you use a web browser on your smartphone, you just type in polllev.com/Erica Burns, and this poll should show up. And then you should be able to just click on your smartphone. Or you can text to this number one of the choices, A, B, C, or D. So which of the following is not a bacterial molecule recognized by toll-like receptors? a couple seconds more. This is good. This is good. 80%, well, it's changing, but 80 some odd percent of the class got it correct. Yay, pat yourself on the back. All right, so double-stranded RNA. Who has that or what has that? Viruses, right? That was our one distractor. Do all bacteria have lipopolysaccharides? No, but some do, and we call those what? Gram negative. Negative. That's part of the outer membrane. Peptidoglycan. Most bacteria, right? That's a bacteria characteristic we learned from the beginning of the course. Flagellin, what is that? That's the protein that makes up the flagella for bacteria, right? So those were all bacterial, right? C was our distractor. That was viral. But again, too, these are very common attributes among bacteria. This isn't going to tell us a specific bacteria because we're still in our non-specific aspect of our immune system, what we call our innate. All right, let's see. How do I go to the next question? I got to remember this. Next poll. That's so easy, right? Anybody could do this. So, which white blood cells phagocytize invaders, dead cells, and debris? Remember to read all answer choices. Is that everybody? All right, no one's indicating to wait. Nobody got this one right. It's all the above. Didn't you hear me say, read all answer choices? Yeah, that was like a major clue, right? They're all phagocytic. They all can do phagocytosis. Now, we really focused in on macrophages, which, you know, doesn't surprise me that that number went way up. I guess I need to close the quiz, huh? No, it's okay. Close the poll. I'm not surprised that you guys homed in on that one. And then remember, these guys differentiate from what cell type? Monocytes, right? So these are basically the same cell. Just this is one in your blood, this is one in your tissues, remember. That's the only difference. Your dendritic cells, we mentioned, right? They phagocytize, but their main job usually is to share the information that they've ingested and digested, right? So we kind of forget that the first step for them, and this is important when we get to our next chapter, is they've got to engulf it, right? They've got to take it in, they got to break it down before they can do the next step, which is presenting, that antigen presentation. So they definitely do phagocytosis. Neutrophils, remember we talked about these guys get called into the area during inflammation. They can do other things, but yeah, they definitely do phagocytosis. If you remember, one of my favorite videos I showed you guys, right, was the neutrophil running around the red blood cells to get to the staph to engulf that bacteria. So the answer is definitely all of the above. So I'm glad I asked this question. I don't get upset when you guys get it wrong now. It's when we take the test. Both of us get upset, right? So we'll clear up these things now, and we won't run into that problem when you take the test. Okay, so let's try our next one. So which class of cytokines do white blood cells use to communicate with each other? And I gotta send it out to you. Activate it, whatever the word is. Push this button. Oh, and I think I'm out of order for my PowerPoint, but that's okay. Oh, crap. The one that I wanted on here isn't actually on here, but that's okay. This is where we both learn. The questions on my tests are tried and true, right? They've been tested. This question, not so much. But that's good, though. Based on the choices, you guys have got this right. But one of the ones I wanted to ask for some reason didn't show up in my poll. So yes, interferons is going to allow the cells to white blood cells to communicate with each other. I was looking more specifically for this one. So notice there's one additional one here. Didn't copy over. I probably didn't. I got confused because there were two inners. Right, interleukins is how the cells is a name. It actually means in between white blood cells. So this one I'd have to really give a specific example to probably key you guys in on the right answer, because there actually are two correct answers, and actually all of them could almost be considered correct answers, right? So because remember, these are substances that are released by white blood cells or other cells to communicate with white blood cells, right? This is all about communication. So in truth, I could change this one to having all of the above and would be the more inclusive correct answer instead of nitpicking, right? And this is where, too, like I said, usually my test questions, right, tried and true. There is really only one correct answer, right? But if we were to run into something like this, you could argue with me and I would give you the points. Right? Okay, so good job on that one. Now this one is more specific if it's the right one, yes. So which class of cytokines tells the bone marrow hematopoietic stem cells to make more white blood cells? There really is only one correct answer for this one. Oops, I gotta send it out to you guys. This is why I said it out loud, because you know I'm gonna forget that button. There you go. Okay, is that everybody? All right. So I screwed you up by the last one. The B's have it. B is correct, right? That particular class is specifically for communication with the bone marrow to determine which set of cells. And there's some clues here, right? Colony stimulating factor, right? The groups of cells are commonly referred to as a colony. Right? So if we want a particular group of cells, we're going to send a particular cytokine of this class to the bone marrow. It says we need more neutrophils, or we need more macrophages, or whatever white blood cells we need. All right. Trying to remember if I have another question. Oh yeah, I do. All right, let me send this one out. I have one last one. And actually, guess where I got this one, y'all? Anyone know? Nope, it's not off the test. The outline. At the end of each chapter, y'all, there are questions. They'd be good ones to read over and try to answer. So here's one. This is straight from the back of the chapter of your book. So all the following trigger inflammation response except. And some of you guys are going, we didn't talk about some of this stuff yet, right? You're right, we didn't. This would definitely be one I would give to you before class, right? I don't expect you guys to get this one right. But let's talk through it, okay? So engagement of PRRs, and again, if you catch me using an acronym on a test, ask me what it is, right? I try to edit most of them out. Again, I literally pasted and copied from the textbook last night this question. So unfortunately, they did not write out what PRR stands for. It's pattern recognition receptors, right? It was in our first slide. So these are like toll-like receptors, NOD-like receptors inside the cell, within the cell membrane, in those endosomes. If those get triggered, is that going to trigger inflammation? Yeah. Definitely. It's one of the major outcomes of these receptors getting triggered. Complement system activation, we're going to cover today, and the answer to that is yes, right? Complement activation is going to usually elicit inflammation response. Tissue damage is the one we already talked about, right? That is going to elicit inflammation response. The one that is not, which I guess maybe you guys looked ahead, because now that one's the winning one, and it is the correct answer. So interferon induction of antiviral and protein. This does not elicit inflammation. When we are responding to viruses, if it's through an interferon response, it doesn't elicit inflammation. Because that just pretty much just brings more cells that potentially could get killed by the virus, right? So we handle that a little bit differently. We're going to talk about that today. And that should have been my last one. Let me just double check by clicking next. It'll probably take me, oh no, this is one for during our, that comes a little bit later in our lecture. But let's go ahead and do it now while I've got it open. So what body fluids contains lysozyme? Oh, it doesn't have the ABCDs. I wonder how come. Is anybody actually texting? Oh, okay. Sorry. You won't be able to do this one. Or maybe it'll add it in, because I forgot to. Ah, there we go. I forgot to click. So this is one of those antimicrobial substances we're going to talk about today. And this is definitely a very beneficial one. So most of you guys keyed in on that, all of the above, right? Although blood somehow ended up below that. I have to edit my poll later. So anybody read ahead? Do you know what lysozyme does? Yeah, it causes cell lysis of bacteria, typically because what does it attack that's found in most bacteria? It's part of their cell wall. Peptidoglycan. This is an enzyme that digests peptidoglycan. So it makes sense that it would be in our tears, right? In our saliva, in the mucus that we produce, in our tissue fluids even, and in our blood. It's even inside of our phagocytic cells. So it's just about everywhere, right? You can think of this enzyme to help protect us against bacteria specifically because it attacks peptidoglycan. So pretty cool enzyme. And remember lysosomes, right? We're talking about digestion. And again, they could contain lysozyme, this enzyme that digests peptidoglycan. All right, so that's it for my polls. I know that for sure today. So what do you guys think? You like that? Good. All right. So I'm gonna continue that, but I probably won't give you some of. Sometimes I might give you some questions ahead of time, like the lysozyme one, right? Is embedded in my PowerPoint, but others I'm gonna not give you ahead of time. So when we talk about our defenses, we can very easily equate it to a security system, as we have been. So your first line that prevents entry, right, your wall for your body is your skin and mucous membranes. And associated with those, as I said I didn't have on my first slide, is antimicrobial substances. So we just introduced one antimicrobial substance. What was that? Literally just took a quiz on it. Lysozyme, right? That's an antimicrobial substance that we produce specifically to degrade the peptidoglycan of bacteria. So there's a few more you're going to learn. And then if they get past that barrier, if they get past the skin and the mucous membranes and the antimicrobial substances, don't stop it, and it gets in. We have sensor systems that detect when stuff has gotten in. So we have those pattern recognition receptors, right? The toll-like receptors, the NOD receptors. We have interferon receptors. In addition, we have complement proteins. This is a system of proteins found in our blood, and this leaks into our tissues during inflammation, right? Because remember, it's proteins in the liquid phase of our blood. So when we have inflammation, remember, you get that fluid that goes in. That fluid also contains the same proteins that's in your blood, right? And complement system is in your blood. So this system can detect, but the cool thing about complement is you notice you can put it in both blocks here, because it's there at the ready in its inactive form in our blood. But it can be activated to actually destroy invaders. Part of the activation, one of the outcomes, is it can literally lyse bacterial cells and other cells. So this guy is twofold, this system. So the interferon response, once it's triggered by the receptors, then it can do something. It can help us eliminate the viruses. Phagocytes, we've already seen them, right? They take on those bacteria and everything one-on-one. They engulf them and destroy them. They eat them up. The inflammation response is important to all of these abilities, especially our phagocytic cells, because only a few of them are there. right? We've only got resident macrophages there. When invasion happens, we don't want just a few cells having to deal with a breach, right? We want as many cells as possible. So we've got to get them to that area, and inflammation response is how they get there. In addition, right, these complement proteins are going to go into the area. Other components of our adaptive immune response, like antibodies, are going to enter into the area. Transferrin enters into the area. What does transferrin do? Yeah, it binds to iron. Remember, iron is very precious. Microbes need it for their metabolism as well, and we don't want them to get it, right? One of the main reasons why we have transferrin in our blood, though, is to help transport, and that's where it gets its name, because iron is not a very soluble substance, so it helps transport it through the liquid phase of the blood. But it also helps keep it away from microorganisms. And then fever is actually a response that can harm bacteria. Fever, in essence, is a raise in the core body temperature. Well, we already learned this, right? Does temperature affect bacteria? Yeah, if you get too warm, we can denature and destroy their proteins and stop them from working. So I was watching the news this morning, and my husband comes running into the bedroom. And he's like, "Did you know?" And I said, "I was listening." But did you know that most of the laundry detergents that you use nowadays are formulated specifically to be used in cold water? And in fact, you decrease the effectiveness of your detergent if you wash your clothes in warm or hot water. Because the enzymes and stuff that are present get changed by the heat. So back in the old days, right? Some of us are that old. They didn't have detergents like that. And in fact, it was better to wash some of your clothes in warmer water. Well, that deteriorates your clothes over time. So they've actually formulated the soaps and stuff that we use, the enzymes in those soaps, to be used at cold temperatures. So again, if you use it at hot, then you're decreasing the effectiveness of your soap. And then too, remember, just raising your electric bill or your gas bill, whatever's heating up your water, right? Because you don't need to heat it up as far as your clothes are concerned. If you're concerned about things that are pathogenic or something like that, blood and things like that, then bleach, right? Use a disinfectant in your wash. So brings me to a perfect segue into, I think I did post for you guys that discussion board assignment I kept saying I was going to post. So remind me, because we're going to take a quick look at that before we end today, show you that. And what you're going to do is, in your home, something you clean with. Could be your laundry detergent. Look up, see if there's any active ingredients in it that actually disinfect. Probably not, unless you're washing with bleach, right? Everybody will look something up at home and answer all the questions, and then you need to reply to your classmates, just like we did with the introduction discussion board. So be able to list and define the first line defenses, including physical barriers, antimicrobial substances, and the normal microbiota. So for our first line defense, right, these defenses, what is your physical barriers? Skin, one more, mucous membranes. And then for the antimicrobial substances, we've already named one of them, lysozyme. And then we're going to talk about the important role of the normal microbiota, the bacteria that are already living on and within you, and how they actually help protect you. So for your skin, there are two major layers that we talk about. We talk about the outer layer, which is the epidermis, which contains a layer of mostly dead skin cells, right? And then you have the dermis layer that actually generates the epidermis layer. And within that, there are several structures that are important, especially being mammals like we are covered in hair. right? Every square inch, right? Some of us work very tirelessly to remove some of it, right? But we are covered in hair. That's the way mammals are. So associated with that hair, in order for it to come out of the follicle, is the oil or sebaceous glands that creates an oily substance known as sebum. And this is to help the hair slide out of the follicle, right? So that it doesn't stay in. The unfortunate thing about that is that it can be a food source for some microorganisms, especially when you overproduce it, right? And under certain circumstances, diet, hormonal cycles, right? Bunch of other things will affect how much of this substance you produce. And therefore, the likelihood of this getting infected. So an infection of the hair follicles, typically we refer to as what? Acne, zits, pimples, right? That's what it is, right? Bacteria are in there growing, right? The pus is when, again, you're getting neutrophils going into the area trying to eliminate the invaders. When you pop those, all you're doing is spreading bacteria across your face or wherever else it is that you're popping it. It's not your best course of action, although I have to say even I fall into that category sometimes of not being able to resist doing that. But then I follow it up with what I should have done to begin with, is put a little bit of triple antibiotic ointment on it. Because again, it is a bacterial infection of your skin, right? So some topical, good old Neosporin. Take care of that stuff, right, for the most part. But again, some people take medications and stuff because it really is related to how much of that you're producing is how often you're going to get those types of infections in your skin. So you have resident microorganisms that do grow in your skin or on your skin. Sometimes sweat glands can also get infected. That's rare. Why do you think that's rare, though? What is it about our sweat that would impede microbial growth? Salty. Yeah, salty. And our skin in general, too, especially when we perspire, becomes salty. And believe it or not, most of the time it's pretty dry. Right? It's a pretty dry environment. So transient flora are going to land on that outer layer, and they're going to be removed when the skin sloughs off, right? So about every 48 hours, you completely turn over your skin, the very outer layer of your skin. 90% of the dust in your home, they say, is your own epithelial cells. And that's what the dust mites are eating. So one of the students in microbiology lab, she got stain on her hand. She's like, how do I get this off? I said, when your skin comes off, it'll come off. Right? As that layer sloughs off, so does the color from the stain that you got on your hands. It's not permanent. Unlike tattoos that affect the dermis layer, right? That generate the next layer. That's why that never goes away. So those guys, right, transient, they're just getting a free ride, right? They're not really taking up residency, right? This can be a serious problem for us, right? And so for disease, our best prevention a lot of times is what? Wash your hands. Wash your hands. Your hands touch everything, right? And they pick up everything and can transmit it to you, right? If you touch something and you touch your eyes, nose, or mouth, those openings, right? Then the likelihood is greater that it's going to enter into your body. Clean hands are your best prevention to infection. So normal flora, right, these residents are more in the dermis layer, in this deeper layer. So what aspects of the skin help prevent infections? We've already mentioned a whole bunch of these, right? The dermis itself is very tightly woven, fibrous connective tissue. There really isn't any gaps, So this is really difficult for microbes to penetrate. Although one of the major openings for us is that hair follicle, right? The epidermis, many layers, and the outermost layer is actually dead cells. They're filled with a protein known as keratin, which is the same protein that's in your hair and nails in higher concentrations. And this helps make the environment pretty dry and water resistant. And the fact that, like I said, you're continually shedding those cells, right? That layer is continually being replaced. So anything that may be associated with those cells also gets sloughed off. Your mucous membranes help protect all your openings. So we're talking about your digestive system, which is actually considered an external environment. It's a tube that goes straight through your body, from mouth to anus. Respiratory, on the other hand, does not go straight through your body, right? It's kind of a dead end. And so that creates a unique problem for stuff that gets in. How do we get it out, right? The good news as it relates to your digestive system, it can go in one end and right out the other end. It has a place to go. Right. Corn kernels, right, are an embryo. It's a single cell. If you don't actually, with your teeth, break that cell wall, then the corn kernel will go in one end and literally out the other. You will see it in your poop. Because you do not have the enzymes to digest that cell wall, the cellulose that makes up plant cell walls. So unless you physically break that, you're not going to get any of the nutrients. It literally goes for a ride, right straight through the system. Right. So stuff can go in, right, and come right back out. So how do we get it from the mouth to the anus? What moves everything through that system? Yeah, peristalsis. It's a muscular system, right? Smooth muscles. You don't have to think about it, thank goodness. Oh my God. If I had to think about it, I'd be in trouble. Right? It's like breathing. We don't have to think about it, thank goodness, right? It just happens. So yeah, just the fact that we continually move stuff through, right? And this is where it can be a problem for people, right? If you don't go to the bathroom on a regular basis, then stuff is staying in. And the chances of it moving from that external environment, your gut, into your internal environment, your body, becomes greater and becomes a serious problem. Right? They say every time you eat a meal, you should poop. They say. Eat more roughage, right? And that's what roughage is. Roughage is cellulose, is plant matter that you can't digest. So it just goes through the system. Right? Helps keep stuff going through the system. And that's what you want. So that whole system, though, is bathed in mucus, which is going to protect your inner linings from invasion, because it'll help trap those microorganisms. And again, the peristalsis that's moving the food through the system that you don't digest, it's also going to move any, hopefully, pathogens you may have ingested, trap them and move them through the system, so hopefully they don't get in, right? They don't invade further. So respiratory, though, that's bathed in mucus too, right? But how do we get that mucus out of there? I mean, it's not a hole through the body. How do we get it out of there? We cough it up, right? But there's actually something at a cellular level that helps us move it. Yeah, the ciliated cells of your respiratory tract, right? They're ciliated. They beat their cilia, and they move that mucus up. You could cough it out, but actually the system is made for you to do what with that? And you're actually doing it all the time and you don't realize it. You swallow it. So guess where it goes? Out the digestive system. Right? And the digestive system will even digest microorganisms. Right? So it'll digest anything that goes through there that it can digest. It doesn't care that it's bacteria, right? Just like people eat bugs, right? You can go to the insectarium, you can eat cookies with crickets in it, right? Your digestive system doesn't care, y'all. It's food, right? There's protein in there. The enzymes are going to digest it. It's protein. It doesn't care where it came from. It's protein. Bacteria, right, are still protein and phospholipids and nucleic acid. You can digest them. You can actually use them as a food source if you ate enough of them. I don't know about you, but I'll pass on that one. But they're good. Some of them are good. Some of them are really good. So urogenital system, same thing. Cilia, right, are moving that stuff out of the system. So that diagram makes me laugh. I don't know. The human body as a circle and tubes. So how are the microbes trapped in the mucus removed, right? So for digestive system, it's all about contraction, right? That peristalsis, that natural stuff that moves the stuff through the system. For respiratory, a little bit more complicated, right? We have what's called the mucosal ciliary escalator. And again, this is because it's moving up, right? So mucus traps it, the cilia move the mucus and the trapped microbes up for you to then swallow and go out the digestive system. Associated with your skin and your mucous membranes, so definitely salt is just for your skin. This one prevents non-salt tolerant organisms, right? So ones that can't tolerate salt. Are there ones that can tolerate salt? Yeah. Staph, for instance, staphylococci. Epididymis that naturally is associated with our skin, hence the name. But Staph aureus, which is a pathogenic organism for some of us as it relates to our skin, that one, both of those guys are salt tolerant. They have to be. They wouldn't be able to grow in our skin if it wasn't for that ability to resist salt. But for the ones that aren't, that helps protect us, right? The salt helps protect us. Some people are like, oh, is that why we have the salt then? Actually, believe it or not, the salt helps with the cooling aspect of sweat. Right? So if anyone ever make ice cream at home, right, what do you add to the ice? Salt. It actually makes it colder. Right? So that's the reason for the salt with our sweat. For some reason, it makes it colder. I don't know the chemistry beyond that, though. To ask one of your chemistry teachers. But pretty interesting stuff. Lysozyme we already mentioned, right? This degrades peptidoglycan, right? So we produce this enzyme, and it specifically will attack bacteria in their cell wall. Peroxidase enzymes, these produce oxygen radicals, right? These are very damaging forms of oxygen. And the reason why these are called peroxidase enzymes, a lot of times they actually take hydrogen peroxide and convert it into these damaging forms of oxygen. The bad news is some microorganisms, and including ourselves, right, we protect ourselves from toxic forms of oxygen. We have enzymes to help protect us, like catalase, that can break down hydrogen peroxide. So this isn't always effective, right, because they may have enzymes that counteract these enzymes. But we can purposely make, especially inside of our lysosomes and under certain circumstances outside of our cells, we can actually make toxic forms of oxygen to try and destroy microbes. Lactoferrin, so again, ferrin in the name, so again, binds iron, but this is the form that's, in our tears, in our saliva, in our mucus, that we actually secrete, and that's why it's referred to as lacto, because it's actually leaving our body. And again, the purpose here is keep iron away from the microorganisms. So, women even produce it in their milk, in their breast milk. Defensins are microbial substances, commonly amino acids, that can insert into the membranes of microbes and disrupt their membranes and kill those cells. So it's like taking little amino acid daggers and sticking them in to the microbial membranes. So we already answered this one. See, it's right on here. I don't know what happened on my poll everywhere. All right, so the answer to this one is all of the above, right? So lysozyme, right, found in our tears, our saliva, our mucus, our tissue fluids, and our blood, and even within the lysosomes of our cells, right? But I just said body fluids here. So things in our saliva, right, lysozyme, peroxidase, lactoferrin, right, these all serve purposes to impede microbial growth in these substances. Our tears, right, we definitely don't want microorganisms living in our eye socket. Your tears actually drain, you're continually bathing your eyes, and then you also have the mechanical action of your eyelids, continually cleaning the surface of your eyes. But the tears that you're continually producing go down your nasolateal ducts. These are commonly referred to as your tear ducts. So they're on next to your nose, right, associated with your eyes. Sometimes, babies and stuff will be born with blocked tear ducts and they'll have to have them repaired or fixed. It leads into your nose. Right? You're constantly flushing that fluid and any microbes you're picking up in your tears into your nose. And then from your nose is actually connected to your throat, right? So it goes, again, into the digestive system. And as I said, we're going to digest it just like anything else. The high acid content or low pH of your stomach, you actually make hydrochloric acid. This is a very strong acid. Denatures a lot of proteins. Very damaging. Most microbes cannot survive this environment. They are going to be killed and digested. And then you have a switch in pH when you go to your small intestine because now you need your enzymes to work, and enzymes are mostly proteins to continue digestion. So now we're going to switch the environment to becoming more neutral by dumping in a whole bunch of alkaline buffers from your pancreas. And that environment is where you're going to continue digestion. The bad news about that, this is where bad guys can get in sometimes, right? If they got past the stomach, right, they could potentially invade the small intestines. Some of them can also invade the large intestines, and in fact, your large intestines has the largest microbial population other than your skin. But this is where your normal microbiota live, the ones that you've developed a symbiotic relationship with. So these guys typically don't cause disease because we're in balance with them. And in fact, you really can't live without them because they help digest some of your food. They help produce essential vitamins for you. And by them being there, they take up the spots in the food, and that becomes less available to pathogens that may come along. So the fact that they're there, taking up that parking spot, eating that food, the pathogens would have to fight for that spot and the access to the food. And your normal microbiota are like, no, I got here first. It's my spot. This is my lunch. You can't have it, right? So it's what we refer to as competitive exclusion, right? They're competing, they're excluding the bad guys by being there. And then, of course, like I said, a lot of them are really good for us. They actually produce vitamins that we need. For women, And the same thing happens with our skin, right? We have microorganisms that are there, that are competitively excluding usually the bad guys. For women, the acidic, low pH, and the normal microbiota of the vagina usually, again, competitively exclude out other microorganisms that could create a problem. So, as I said, they're taking up the spots, they're eating the available nutrients. Some of them even produce toxic substances that impede pathogens. So, Propionibacterium, these guys degrade lipids and produce fatty acids. So they'll eat the sebum that we produce, that oily substance, and they'll produce fatty acids that are toxic to pathogenic organisms. E. coli is found to synthesize substances we refer to as colokines. And these, again, are inhibitory to pathogenic organisms. Lactobacillus actually produces acid, and that's what helps maintain the low pH in the vagina for most women. When you get disruptions of these, you can even get disease or infectious states. So Clostridium difficile, this is a spore former. You're exposed to the environment. You ingest it. But most of the time, it doesn't take up residency in your intestines because it's excluded, right? It's all the other microbes are there. They're taking up the spot. They're taking up the food. It's when you have a disruption of the normal flora in the intestines that you usually get an infection with Clostridium difficile. And so usually overuse of antibiotics or some other condition that's wiped out your microbial population in your intestines predisposes you to this infection because you don't have that level of protection of competitive exclusion. And actually one of the ways they treat this infection is to give you a transplant of someone's poop from your house, right? Because you usually have the same microbes in your guts. To try and reestablish that microbial environment in your gut to exclude out the Clostridium difficile, which will literally eat your intestines. It is a horrible bacteria. And then women have experienced Candida albicans infections. If you're a lucky woman who's never experienced that, you are just that, very lucky, because it's rare to not experience that in your lifetime. And of course your life isn't over, so it could still happen. And why does it happen, right? What happens, what a yeast infection is actually just an overgrowth of the normal yeast that are associated with your skin, and for women, your vagina. Under circumstances, it overgrows, and that becomes very uncomfortable. Why is it able to overgrow? Well, maybe there's been a disruption to the bacteria like the lactobacilli. Antibiotic treatment. For some women, hormone fluctuations can change that microbial population because it will affect them as well. And so you don't have the bacteria there to keep the yeast in check, and the yeast overgrow, right? They take up all the food, and they overgrow. Diabetics deal with yeast infections a lot. And you can get yeast infections of your skin as well, right? Because again, they're normally associated with your skin. They like warm, moist environments though. So the vagina is like, the wind. They're so excited. It's warm, it's moist, right? It's happy, happy. And then plenty of food, forget about it. They're going to grow like crazy. So a lot of times that happens, right, when you have this disruption or they have an excess of food and they can overgrow. So then we just got to knock them back down, right, get them in check, get the environment going happy again, and then we're all happy again. So these are what we refer to sometimes as opportunistic infections too, where your own microflora, right, are causing the problem for you. So same thing with E. coli, right? If it gets somewhere other than the intestines, if it gets into the vagina, into the bladder, right, it can cause problems. And your best protection against bladder infections, anyone know? Water. Drink lots of water. Because that action of going pee flushes out whatever's in there, right? So if you keep peeing, it can't stay and take up residency, right? Drink lots of water. Make sense? Pretty cool, huh? So we've already talked about the outcomes of toll-like receptor engagement, right? Most commonly is going to be inflammation, right? Because this is the sensor saying, bad guy got in, come help. The next system we're going to look at is the complement system. And so again, we really want to focus in on what happens when we activate this system. What are the outcomes? So I'm going to take a break for a minute and play, hopefully.
Regardless of whether the complement system is activated by the classical, alternative, or leptin pathway, the activated complement proteins are involved in several important processes associated with host defenses, including inflammation, attraction of neutrophils, opsonization, and cell lysis. Complement C3A participates in inflammation by inducing changes that cause the walls of local blood vessels to become more permeable. This facilitates movement of phagocytic cells from the circulation into the tissues. Complement 5A induces a directed chemotactic migration of phagocytes to the site of complement activation. Complement C3B functions as an opsonin. It binds to microbial cells, making them more susceptible to phagocytosis. Complement proteins C5b, C6, C7, C8, and C9 react together to form a hole in the cell membrane. When C5 convertase converts C5 into C5a and C5b, the C5b binds to the cell surface and combines with C6. C5b6 binds C7, enabling it to insert into the membrane. Binding of C8 is followed by binding of several C9s. The hole generated by formation of this membrane attack complex causes the cell to lyse.
So it can directly lyse cells. But notice this is a membrane attack complex. What is it inserting into? A membrane, right? This is great when you talk about gram-negative bacteria, because what do they have? The outer membrane. Gram-positives, though, they've got what protecting that membrane? The cell wall. So these proteins would have to travel through the cell wall to get to that membrane. So it's not as effective against gram-positives as it is against gram-negatives, because this can insert into their membrane, in that outer membrane that they have. So complement system is a series of about 9 proteins. So C stands for complement, and then they're numbered. And they're numbered in the order in which they were discovered, not necessarily in the order in which they're activated. But the good news for you guys is you're not going to memorize this cascade. This is not a graduate level immunology class. At one time I had it memorized. I don't even have it memorized anymore. Right? It's a waste of space in the brain. Okay? You can look it up in a book. But there are important aspects of it. There are parts where they break into pieces. And when they break into pieces, those fragments are then giving another letter designation, A and B. And there are a couple of these guys that, yeah, you do need to memorize. And, of course, I still remember them because they're major key players. You saw them in this animation. You've seen them before when we talked about phagocytosis, right? Because they're important players in this. And so, again, what we want to focus in on is this activating of this system is going to help inflammation, right? It's going to cause those blood vessels to become leaky. It's going to call those white blood cells to that area. One of the substances is an opsonizer. It actually binds to the bacteria and makes them more accessible to phagocytic cells, because phagocytic cells have a receptor for that complement protein fragment. And then as you saw, they can form that MAC complex that literally can lyse cells. So these are our important outcomes, right? We're going to get inflammation, we're going to get opsonization, hopefully, and maybe even lysis of the foreign cells. So the important components we need to know, because they were major players, right, was C3A and C5A. Those were the ones involved in the inflammatory response. The opsonizer was C3B, and I always remember B for binding, right? It literally binds to the surface of the bacterial cells, and then our phagocytic cells, notice the receptors they have, so they literally grab onto that. When something is tagged, right, when a component of our body binds to something else and basically tags it for destruction by our phagocytes, that's referred to as opsonization. There's one other molecule that our body produces that's going to tag for destruction. It's going to opsonize. Anyone know what it is? We make it against specific pathogens. It's part of our adaptive immune response that we're going to go to. Nope. It's a protein produced by our body that will specifically bind to specific pathogens, viruses, bacteria, antibodies. These numbers, thankfully, numbers and letters you don't have to memorize, right? You don't need to know that C5b and C6 and C7 and multiple C9s and C8. But what you do need to know is the name of this complex, right? This membrane attack complex, and again, commonly abbreviated MAC. Not like the Big Mac, right? We're talking about membrane attack complex. And as we've already discussed, right, why is it more effective against gram-negatives? Because this inserts into membranes. And what membrane do they have? What do they got? That outer membrane, right? Where for the gram-positives, it's got to travel through that cell wall to get to that membrane. So this is literally, right, these dark spots are holes made by membrane attack complexes inserting to a membrane of a cell and destroying it. So I'm not going to play this animation, but I definitely want you guys to look over it for next time. And so notice that was the outcomes, but how do we get this started? Right? And so it's going to mention some things that I just mentioned, right? And we're going to go over that next time. We just got a few things left. I will post the next PowerPoint, and we'll finish up this one. I want to jump over just real quick to remind you guys something I mentioned earlier. In our modules, you will notice, or maybe not, because I did, it's right there, yay. Except the due date is way wrong, or is it, yeah. Oh, that's the page. It didn't add. So let me do that right now. I activated in discussions, I didn't activate it here. There we go. So it's in Module 1, right? I'm going to put it at the end of it because it's still related to Module 1 material, but we haven't finished up. So make sure you do this discussion board. I know it's been a while since we've done a discussion board. I really want you guys to include these questions in your answer so you can literally highlight, right? Right-click, copy, in your reply. Oh, look, Connor already did it and rocked it out. Thank you very much. Look at that. So what the product is, right? And then what you use it to clean with. Why did you choose this product to clean, right? List any active ingredients, right? So look, enzymes and such, right? But are we disinfecting? Probably not, right? Yeah. So you got to determine. But in this case, right, one of our options too can be doesn't disinfect at all. So the answer is it's not any of these. Right? Because remember, these are terms for disinfecting if you're actually killing microorganisms. And truth is, most of the soaps that you're using Probably not. Probably not. All right. So you can go back and change it too, you know. I think you wrote. Yeah. So yeah, it doesn't disaffect. Yeah, I don't see why not. I'll have to reevaluate maybe. But, okay. She asked if the test is still the scheduled date. I'm shooting for it. We'll see if we make it. Okay. All right.